Physics students, good afternoon. Mr. Fugit here. As you saw in the last video, I'm in my 90s attire today, so you're catching me dressed a little bit down. But today we're going to be looking at another pretty simple problem involving projectile motion. This video is going to cover really the second part of a two-part problem, which is the second problem on your homework. This is kind of part 2 of 2. So if you didn't go through part 1 or watch that first video, or you don't feel comfortable with that first problem, make sure you get there first, because we're going to be drawing on some of the work we did previously. So question 2 asks us this: find its horizontal range, neglecting air resistance. So if you remember from problem 1, we're looking at the artillery shell that's being launched on level ground. So I'm on level ground and I'm launching an artillery shell. I was given a velocity of 1,850 meters per second at an angle of 30 degrees. And what we were told was that our projectile was just going to travel along its trajectory, and at some point hit the ground again. In this part number 2, we're asked for how far that object travels horizontally. Remember that term range just describes a horizontal distance. So now we're looking for how far our object travels horizontally. So I'm going to list out my variables just one more time from what we had from problem number 1. Delta x, initial velocity in the x direction, v1 in the x direction, acceleration, and time. Now time was something we solved for in problem 1. You will need that here in problem 2. So if you haven't done that, make sure you go back, watch that video, and feel good about solving for time. So our time was approximately 188.6 seconds. My acceleration in the x direction will always be 0 meters per second squared. I'm going to show you one more time just how to find our velocity in the x direction by using our velocity vector that we're given at the beginning. Now for the vertical direction, because remember, when we're dealing with projectile motion, we have to take into account both directions here, horizontal and vertical. Our delta y was 0 meters because we were launching and finishing at the same point. There was no displacement from start to finish vertically. I began and ended at the same point. Initial velocity in the y direction we found to be 925 meters per second. Just using our angle and the initial velocity we were given. Final velocity in the y, we weren't really given that value and we weren't asked to solve for it, so we're not going to pay too much attention to it here. And acceleration in the y was negative 9.8 meters per second squared. My time, as we solved for previously, was 188.6 seconds. That is something, if you'll remember, that is always going to be the same in both directions. So what we're looking for in this problem is, what is my horizontal range? Effectively, how far is my projectile traveling? How far is my projectile traveling in that x direction? Now you'll notice it looks like we don't have quite enough information to solve for that. So what we're going to do is we're going to break down that velocity vector into its horizontal component. So I'm going to come to a new page just so it's nice and clean. I'm given to start a velocity vector. Remember, your numbers are going to be a little bit different, but the process will be the same. My overall velocity vector, 1,850 meters per second at an angle of 30 degrees. What I'm going to do is, as we have with many vectors, I'm going to break that vector down into its components. We know that any vector has an x component. Since this is a vector of velocity, we'll call this v0 in the x direction, initial velocity in the x. From our previous problem, we already know our initial velocity in the y to be 925 meters per second. So here, what we need to do is we need to use maybe our trig functions to solve for that x component. So if you'll remember our acronym, SO, CA, TOA, which helps us remember which trig function might apply. Here, I have an angle, my hypotenuse, and I want to find my adjacent side. So adjacent and hypotenuse is going to be my cosine function. So here what I'll do is I'll write out my function. Cosine of 30 degrees is equal to adjacent over hypotenuse. CAH. Now, what is adjacent is my initial velocity in the x, so I'm going to plug that in, which we don't know, v naught in the x direction, and we do know our hypotenuse. That is the 1,850 meters per second. Now that I'm here, if I want to get initial velocity in the x by itself, I need to get rid of that 1850 on the bottom of my fraction. So I'm going to multiply by 1850 on both sides of my equation. And when I do, this value on the right will cancel out, and what I'll be left with is an expression that resembles this. Now that these values are gone, I'll have v naught in the x direction, just going to rewrite this, is 1850 cosine of 30 degrees, similar to what we did in problem 1. So if I plug this in, 1850 cosine 30, make sure we're in degree mode. My initial velocity in the x direction was 1,602.1 meters per second. So now I've just used what I know about trigonometry and my given velocity vector to find my initial velocity in the x direction. So now that I have that, I'm going to come back over to my list of variables and write that in. 1,602.1 meters per second. Since our acceleration for a projectile motion problem is going to be assumed to be 0, that means our initial and final velocity are the same. Remember, acceleration just measures how much our velocity is changing. If there's no change, our starting and final velocity must be the same. So now I have a lot of variables to help me find out about delta x. Now at this point, since we have all 4 variables, if I look at my kinematic equation sheet, it might look like I can solve for any of them. The best one here, if we're trying to find range, is to use equation number 2. So I'm going to write that out. Equation 2 looks like this. Delta x is equal to initial velocity in the x direction times time plus 1/2 acceleration in the x t squared. Now that I'm here, I'm just going to list out the variables that I know and plug them into my equation. So delta x, we don't know, we're looking for it. Initial velocity, we found that was our 1,602.1 meters per second. Okay. I know my time value, that's what I solved for in the previous problem, 188.6 seconds, plus 1/2. Well, my acceleration in the x direction, remember, that's going to be 0, times 188.6 seconds squared. So if you'll notice, at the very end of our equation, acceleration in the x is going to be 0, so regardless of my other values, that's going to cancel out to be 0. Make sure when we plug in a value for time here that it is in seconds, because our velocity is in units of meters per second. We need to make sure those units of time match. So this value gets canceled out on the far end of my equation. I'll be left with delta x is really equal to this portion right in here, 1602.1 times 188.6, my velocity times my time. So I'll take 1602.1 times 188.6, so I'm going to get a pretty large value in here. I'm just going to write it all out. 302.137.8. Okay, this is a delta x value. So this is going to be in meters. Okay. Now, since our problem doesn't specifically ask us for a unit, we should be able to present this in meters or kilometers. So when you plug this into Quest, make sure you plug in your unit. If you want to leave this in meters, that's just fine. If you want to convert this to kilometers, you can divide that by 1,000 or move our decimal 1, 2, 3 places left, and our delta x would be 302.1 kilometers. Either of those would be appropriate units to present. Okay? If we're not told a certain unit, we can plug in either one as long as we put that unit into our equation, or excuse me, into our answer box on Quest. Okay? So hopefully this gives us a little bit more direction. Remember, don't try and solve part 2 unless you've solved part 1, because we're going to need that time value. Okay? Good luck.